Welcome, everyone. My name is Michał Stęchły, and I am quantum software engineer at Zapata Computing. And I would like to tell you today a little bit about the job of quantum software engineer, and specifically to give you an example of what my job looks like on a daily basis. So a little bit about me. So as I said, I work as a quantum software engineer at scientific software team at Zapata Computing. I'm involved, given that Zapata is a startup, I'm involved in many different things. So from product development, a little bit into research, but also sometimes helping with the customer projects. I'm mostly interested in variational quantum algorithms and optimization. And apart from that, in my spare time, I'm running a mentorship program at Quantum Open Source Foundation. I write a blog and recently also a podcast about quantum computing. And in general, I try to help get people on the next level with the quantum computing. Okay. So I wanted to also say something about Zapata and Orquestra. Just if you don't know. So Zapata is a quantum software startup, and we have offices in Boston and Toronto, but also many people remotely. And specifically, I wanted to tell you what Orquestra is, because I might be referring to that throughout the presentation a couple of times, so that you are not lost. So Orquestra is a workflow management system for quantum computing that we have created at Zapata. And basically, it allows you to express an algorithm, express the computations you want to run as a workflow that you can then run on a cluster that can connect to different quantum devices. And that's basically it. So if I mention Orquestra workflow, this basically means, well, algorithm written in a very specific format that we are running on Orquestra. If you want to learn more, there is more on our website. I hope this will be published on YouTube afterwards, and in case someone is watching this on YouTube, I will provide the link to this presentation so that it can be under this video. And other people who are right here, right now, also would be able to refer to that. Okay, so let's get into the topic itself. So what's the role of a quantum software engineer? The way I see that is that quantum software engineers are people who are bridging the gap between science and software, mostly by creating tools for scientists, but also creating tools like from what scientists did, so that other people can use it. So two examples of that. One is a situation where scientists wants to run some algorithm, but they would like to run it on a specific simulator, and we are writing them the integration for that simulator. Well, making sure that the simulator works correctly in your environment, that you have all dependencies installed, and so on, is not really particularly scientific. It's mostly software task. So it makes sense so that software engineers do that and scientists focus on the research. And on the other hand, also someone comes up with an algorithm or a new method, and then we take this algorithm and just make sure it's easy to use for others. So we make sure we are checking there is like proper documentation. We make sure all the tests are in place. We make sure it actually covers all the cases that it should. And I'll show you examples of what I exactly mean by that later on. So how this job is different from a job of a researcher or a scientist? Well, it is very different, because mostly it's about writing software. And I talked with many colleagues in various companies that have similar positions. And across the field, it's pretty consistent that 80% of their time they spend on writing software, and maybe 20%, maybe less, on doing some science and research. It's not the regular software engineering job, though, for many reasons. One of that is that I think the domain knowledge is much more important here than it is in, for people who are writing web applications for, I don't know, banks or for e-commerce or stuff like this. It's quite different. We also are working very closely with scientists, which is really nice, but also, it's kind of specific type of cooperation. We need to have very high resilience in this job because the field is very new, and there are, it's still evolving. So often you write some code and it turns out not a long time after that actually it's no longer important, like no longer useful, because either our understanding of some concept was wrong and we just got the science wrong, or that someone released some new results recently, and basically now we have better methods. So often it's about 2 steps ahead, 2 steps forward, 1 step back, just because the field is changing so quickly. It also involves some DevOps work, like setting continuous integration pipelines. Like recently, I've been writing GitHub actions for our repositories so that we have automatic style checks and much more. One thing that I wanted to emphasize is that it is a team effort, and the amount of domain knowledge that one's need is really big. So here is our team. You can see who has like degree in what, and also like what's our specialty and background. And this slide here is to show a couple of points. So first is that there is not a single person that knows all of that, and we rely on each other. The second is that we have complementary skill set, and we can, by working together, we can really leverage one's knowledge. So for example, Konrad is a very good Python programmer, and whenever we have some problems with how to do something in a really elegant or efficient way in Python, then like we ask Konrad. But for example, given that Max has a background in material science and chemistry, then whenever we need to write some code in that domain, well, the Max is either the person that does that, or actually just the person that helps us understand the domain better. And also I wanted to point out that even though this domain expertise is super important, we have on our team Alex, who actually has no background in, or at least not official background in physics or quantum computing, and he's learning this on the fly, but his expertise in machine learning and also just all sorts of software engineering makes him really valuable person in our team. And I have a podcast called Noisy Intermediate Scale Podcast, and the first episode was exactly about this topic, so what quantum software engineers do. I talked more about the challenges that we face, some typical types of tasks, what are job requirements, and much more. So if you're interested, you can find it online and listen to that. But today I didn't want to just say all the things that I already said there. I wanted to give you an actual example of what I was working on recently. So I will show you the code that I've written. I will walk you through the process of writing this code so that you can get better understanding of the whole process and of the actual, what this job entails and how does it look like. Okay, I'll just have a sip. Okay, so today I would like to tell you about our implementation of warm start QAOA Ansatz. And I've chosen this particular project for a couple of reasons. So first, all the code that we have written for that is open source. So I'll be showing it throughout the presentation. You can also find it on GitHub. And this is something I worked on recently, so I remember pretty well how it looked like. I don't like to talk publicly about projects I did half a year or a year ago. It's a little bit more on the scientific side of what we do rather than regular software engineering. So I thought it will be more interesting for you. And also we did this in the cooperation with the research team. So I can also show you a little bit how such cooperation looks like. So how we quantum software engineers work with the research team. And here we have the paper, and I hope you see not only my presentation, but now right now my browser as well. So there was this paper, warm starting quantum optimization, and by this fine authors here. And you will see that throughout the presentation, I will be showing some snippets of text or equations from this paper. So if anyone is interested, this is where they can learn more about the algorithm itself. And before we actually start, I wanted to warn you that this talk is about the software and not the science. So if you would like to get a deep understanding of the algorithm itself, the methods, well, that's not here. Just go and read the paper. Here, I will show you the process of changing the paper into the code, but without actually getting very deep into the scientific and algorithmic nuances, only as much as it's necessary to explain the concept. Okay. So it all started roughly in December 2020. And as you can see, we have a researcher here in the left corner who has some ideas. And you can see quantum software engineer just squashing some bugs in the bottom right corner. And basically, at some point in December, guys from the research team came to us and said, we would like to use warm starting QAOA for one of our projects, and whether we could help them with the implementation. And like, yeah, sure, of course. What's the timeline here? And they said, well, we want to have it ready around the beginning of the April. So we said, well, it gives us roughly 4 months to work on that. So yeah, that's a very reasonable request. And the first thing here that I wanted to highlight is, at least at Zapata, it usually works this way, that the scientists know in advance what research they want to do. And if they come to us and ask us to help with some implementation, they actually do that ahead of time. So we can all prepare better and schedule, our job, our work in advance. And that's pretty important because, as it turns out, often these things take longer than one expects, as we will see. So yeah, just send me paper and we'll talk about it. So how it looked like. In December, we got a rough plan of all that we needed for this particular project. And that was not only the warm start part that I'm talking about. There were like some other features that they wanted to use in the research, and that required a lot of different things to implement. So we started implementing these features one at a time. And basically, we had a huge list, not that huge, but like a list of all the things that they wanted to have in our software, and we're just every week taking one of them or not, and just going through that list so that we will be ready with all the parts for the beginning of the April. And also we had a weekly meetings to stay in sync about the software and about the needs of the research team. So basically, we are meeting every Wednesday or Thursday for half an hour to just talk. Okay, so research team is doing research on this and that, and they actually something changed and they need this part earlier, or they actually this other feature is no longer important because something changed and they realized it's actually there are different ways to solve this problem. And I'm giving them updates on like where we are on the software side of the things. So the first phase of that was planning, and actually that wasn't very complicated in this particular case. And for the particular feature of warm starting QAOA, well, I just needed to read the paper, talk with the team to make sure what's the scope of the project and whether we have to implement the whole paper or just like part of that, and then just code it. So it's not particularly complicated plan, but it was worth just going through the steps to make sure everything is okay. Okay, so let's talk what is the substance of this project. So what the warm starting QAOA is even all about. So before we start, actually what the QAOA itself is. So if some of you don't know, the QAOA is a quantum algorithm which allows us to find the ground state, the solution to so-called Ising problems. And as it turns out, we can express many combinatorial optimization problems like traveling salesman or graph coverage problem as Ising Hamiltonians, as Ising problems. But since Ising problems are equivalent to quadratic unconstrained binary optimization problems, so QUBO, we can translate these problems to QUBO as well. There are like basically two representations of a similar thing, and sometimes we prefer to use QUBO, or sometimes we prefer to use Isings. And one property that both these problems have is that they are both binary problems. So the output, the solution to the problem is just like 0 and 1, or in the case of Ising, it's actually -1 and 1, but that boils down to the same thing. And well, the problem of the integer problems is that they are often harder to solve than continuous problems. So if we have this little function on the right, you can see that if we just like draw the whole curve, it has this shape, right? And we can use some nice methods, well known, like gradient descent, to just start from any point and just get to the bottom of that and see that the minimum value is at x equal 0.6. But if we say that we want to solve this problem not in the realm of the real numbers, but in the realm of integers, well, it's only defined from the integers on 0 and 1. And this is a toy example, but it's not that obvious how to, maybe not that obvious. There are like very different methods for solving this type of problems rather than continuous variables problems. So one thing that people in the traditional, like classical optimization world figured out is, hey, maybe we can relax this integer problem into continuous variable problem. So instead of saying, the only viable solutions are those given by integers, we say, actually, we can use any real numbers we want, because this will make this problem easier to solve. And then we'll use the solution we obtained from the relaxed problem, so this 0.6, to somehow help us get the better solution for the integer problem. And indeed, if we just go with the very, very simple and naive method of just rounding the continuous solution, so if we take 0.6 and round it, we will get 1, which is the correct minimum in the domain of integers. Well, this is very contrived and simple example, but it's one idea of how to deal with this type of problems. And the main idea of the paper is, like people used it in the classical optimization for quite some time, so why don't we just use it in QAOA and see how it works? So that's basically it. So when it comes to planning the, after reading the paper and talking with the team, we decided that what we need to do is A, implement the warm starting QAOA Ansatz. And if you don't know what Ansatz is, I will explain that in a moment. Then B, write code which will solve the continuous relaxation of QUBO. So as I said, continuous relaxation means that we take solve the problem not in the integers but in continuous variables, so like real numbers. And then we needed to write an orchestral workflow to run this code. Now, I won't be talking about the last part because it will require too much of actually explaining how orchestral works. So we'll focus on the first 2 points. Okay, so first thing, Ansatz. If we go to the paper, we'll see that one version of the Ansatz looks like this. And, well, it doesn't seem particularly complicated. It starts with some initial state, so rotation y of like theta, and we have theta 1 to theta n, so basically a vector of thetas. And those thetas are some angles that are calculated based on the solution of the relaxed problem. Okay, so we first solve the problem in a continuous variable way. This gives us some numbers, and then we translate these numbers to thetas. So that's what's it. And then we have standard QAOA construction, which is some subcircuit based on the cost Hamiltonian, defining the problem, parameterized by the angle gamma, and another part called the mixer Hamiltonian, like mixer part, associated with the angle beta, right? And then we just repeat this whole thing p times. So p is number of layers. So one could think, well, that looks like super easy implementation, right? Because we just need to write something that looks like this, right? So we create a circuit, and we start with the layer of Ry gates, and then we add, exponentiated cost operator, and then a layer of Ry, Rz, and Ry. And actually, I just realized that I totally messed the gates here, so please don't worry about it. It should be Ry, Rz, and Ry, and the parameters are also wrong. But that's basically how one would approach solving this particular problem. But actually, it's not that easy, and I'll show you why. If you were to just write your own small project and you didn't care whether other would have hard time or easy time using that, then you could just write something like this and that would be good. But actually, with Orquestra, we have defined some structures, some objects that allow us to get much more of that. So implementing such Ansatz, requires a little bit more effort, but actually it pays off very well in the future. So what I'm talking about is something I call Ansatz interface. And if you can see my browser, please kind of react or let me know in the chat or something, because this is pretty crucial.
Yes, we can see it.
Awesome, thank you. So here we have something called like a class, an abstract class, Ansatz. And this class defines an interface of how we want all our implementations of the Ansatzes to look like. So you can see it has like some init. It has a couple of functions, a couple of methods, right? And maybe the first thing is, okay, why would we do that? Why would we create a base class called Ansatz instead of just everyone writing their own Ansatz classes? So the reason is that, let's say we want to compare two Ansatzes. So we want to give the same problem and basically give the same inputs, use the same simulator, use the same optimizer and everything, and just compare how regular standard QAOA Ansatz compares with this warm start QAOA Ansatz. So the problem is that if we implement it in a way where everyone can implement their Ansatzes as they want, they might implement them in a way that they have different interfaces. So the functions have different signatures, and they take different objects as input, and so on and so on. And they also return values in a different format. So in order to unify this, we create interfaces like this. So for example, let's take a look at the parameterized circuit method here. So this method, well, when we just call it on the Ansatz object, it returns a circuit. And what it does is that it allows us to have a mechanism to not calculate the circuit for the Ansatz every single time. So some Ansatzes require some extra computation in order to calculate how the circuit looks like. And so this might be pretty, computation heavy and time intensive, not extremely, but still you might want to save that time. So what we do is that we check if the private field of this class parameterized circuit is none. Then we create such parameterized circuit with the generate circuit method. However, if it's not none, then we just return the parameterized circuit that has been already created, right? And also, as you can see here, this is for creating parameterized circuit. So the circuit that doesn't have the actual numbers inside. So the beta and gamma angles are just symbolic parameters. So if it doesn't support symbolic parameters, then it throws some exception. And the important thing here is also that what happens if the number of layers or the cost Hamilton, something changes, maybe just something changes in our parameter, number of layers, and well, then we cannot use this parameterized circuit that we already had calculated, right? Because, well, it changed in the meantime. So now if we just change the number of layers, we need to recalculate the circuit. And the nice thing is that the way we coded it is that this number of layers is defined as Ansatz property. And if we ever change the number of layers, then it sets the parameterized circuit to none. This code is in one of the helpers, so it's not here. But then we know that we need to recalculate the circuit. And this all is in the base class, which is an abstract class. So every class that inherits after this will actually have this mechanism built in. So it's super convenient because you don't need to worry about it and write this logic every single time. Okay, so, and also you always know that if you call a get executable circuit method on your Ansatz, you will get a particular output, and it's not that you have different methods called get circuit, get executable circuit, get circuit with parameters, and so on. So it's nicely unified. And so that's one benefit. The other benefit is that we have tests for all that. So we have a base class with tests, and actually we can check all the things, like some of the things that I talked about. So for example, we have this test set number of layers invalidates parameterized circuit. So we check whether if we set the new number of layers being 100, whether this private field parameterized circuit is actually none. And we can inherit these tests for the children classes as well. And this way, we know that all the ansatzes that we'll implement later actually pass this basic test here that we defined. Okay, so just as an example, this is a standard QAOA, so like Farhi, the one defined in the original Farhi's paper. And it has cost Hamiltonian, it has mixer Hamiltonian, and basically it generates a circuit based on like how it was defined in the paper. And as you can see, this implementation itself is not that big. It's roughly 80 lines or so, because a lot of the logic that we had is in the base class, right? So we didn't have to write the parameterized circuit method because it's already implemented in the base class, but we just did have to implement the generate circuit method. Okay, so now let's take a look at the actual warm start ansatz that is what we care mostly about here. So you can see that we have cost Hamiltonian and we have thetas. In the Farhi ansatz, we had mixer Hamiltonian defined, so we could pass the mixer Hamiltonian. But here, well, the mixer Hamiltonian is always the same. It's defined by thetas, so we just use thetas. And here we have the code for generating the circuit. And as you can see, well, it's slightly, this is basically the snippet that I showed you here. It's just a little bit more involved because, well, we check whether the params are none. We do some, bookkeeping, and the syntax is slightly different, but that's basically the same thing. And of course, once we got that, well, we also have to write tests for this, right? So here we also have tests. As you can see, they inherit after the base class, and well, we just test whether whether it works. But this is like if you have written code without writing tests, you have not written the code because you don't know whether it works. So this is how the tests look like. And when it comes to implementing the ansatz, well, that's basically it. Like that's the whole thing that needed to be done. So, oh, there was like one little one more thing. So we also need to have a method which somehow converts the C, which is like the solution to the continuous relaxation, into those thetas. And well, it just looks like this. And this is from the paper. So they said, okay, we decided to do the conversion this way for the following reasons. And I just took this and implemented this as a bunch of if-else statements. that's it. I mean, that was pretty straightforward thing to do. Okay, so now we get into the third phase. So first was planning, second was implementing the Ansatz, and third is actually solving the relaxed QUBO. So the starting point for this part of the project was the code I got from my colleague Guoming that he used for this particular problem, and this code was using a CVX_opt package. And while the code was doing the job it was supposed to do, and it was working properly, it had a couple of issues that we had to solve before incorporating that in our code base. So first was that it used a custom QUBO class, and actually in our framework we use the QUBO class defined in the dwaves library Diamond. So there was a little bit of refactoring to make sure that actually his code uses the class that we are using in the rest of our code. Second thing was that he was using some custom CVX_opt data structure, which also wasn't a particularly good idea for the production development, for the production code. And also there were some assumptions hidden in the code that we wanted to state explicitly, and for example check whether given parameters have values from given range or different things like this. Well, it turned out that this part was harder than I expected. So the first challenge was to decide whether to use what package for convex optimization to use. So there are two packages in Python. I would say like two most popular packages for this. One is called CVX_opt, so convex optimization, and the other is CVX_py. And Guoming started from CVX_opt, and later he discovered this CVX_py, and he was wondering which one we want to use. And we could use either of them, but we had to choose one of them. So how do you choose what package to use? So here I will just walk you through my method of doing that. So I go to GitHub and I look how popular the package is. So we see that CVX_opt is slightly less popular. I mean, maybe not slightly, but like less popular than CVX_py, looking at the number of stars and forks. But that's only one part of the story, because maybe one of these packages is just 5 years old and the other is 1 year old. So this doesn't give us enough information. So the next thing I usually look at is the releases. So how often the new versions of this package are released, and also how actively it's being developed. So as you can see, the CVX_opt, the last release was in February, and I was making the screenshots like 2 or 3 days ago. So this one was still in March. So it looks like this is the CVX_py is being released more often, and also it has many more releases. It also has many more commits, and actually, as you can see, the last commit on the CVX_opt was the same time as the last release, while CVX_py is being maintained regularly. In addition to that, CVX_py had more examples in the documentation and basically just cleaner docs. So I decided to go with CVX_py. And this is pretty important because I was both in situations where I've chosen a package without too much thinking and looking, there was a good package that seems as a very reasonable solution, but I haven't noticed that it's no longer maintained. So when I hit a problem or found a bug, there was no one there to help me, and there was no one to answer my questions. While I also been in the situation where the package is very well maintained, and basically, I ask a question and I get response, and that works very well and makes just development so much easier. So the next issue with this part of the code was that what's the representation? Not even representation. So you'll see. So we defined QUBO as the following problem. X is the binary vector of that represents our solution, and sigma is a matrix, and mu is a vector. So we basically want to minimize this number here. And this is the definition of QUBO in the binary variables. However, if you want to relax it, there are different ways to allow for the relaxation. So one of them is that if the sigma matrix is positive semi-definite, we can just say that we minimize this part here. So x sigma x. And as you might see, we don't include the mu term, and don't worry about it. We'll talk about it in a moment. Right? And basically, we have problem like this. X is now not a vector of either zeros or ones, but the vector of the values from 0 to 1. And we can use this with the classical, solve this problem with the classical optimizer. That's fine. But also there is another way to get the solution, which is called semi-definite programming. And it does some magic. I don't fully understand how it works, to be honest. But basically, there are two methods presented in the paper how to get the continuous relaxation. And the problem is that, well, the one is called semi-definite programming, and the other checks whether the matrix you have is positive semi-definite. And well, these terms are dangerously kind of similar to one another. And when I was reading that, and when I was talking with Guoming about it, I got totally confused. And I was mixing the SDP with positive semi-definite. So you can abbreviate that to PSD, but actually in my head, for some reason, I was calling it semi-positive definite, so SPD. So in my head, this was SPD and this was SDP, and I just got confused. And I was reading this, I was talking to Guoming, I was reading the paper, and I couldn't understand what's happening because everything that he said was making no sense to me after I read the paper. And I didn't know whether we want to implement the SDP case or SPD case or something else. And finally, in one of the conversations we had, he pointed to me out that actually this is probably the thing that I'm confused about. And then I realized that, oh, indeed, so like the positive semi-definite thing and the semi-definite programming are two things. And right now, when I look at this, to be honest, like it's pretty obvious, and they are not even using any abbreviation here, and like it's positive semi-definite, so there isn't even place for the abbreviation like SPD that I had in my mind. So I just got confused, and I wasted a good couple of hours just trying to understand what's happening here. And I'm talking about this just to show you that these kind of things can often just be confusing, and you might not have the full understanding of what you are doing. And it's important to have someone that actually understands this problem really well, if you are not such person. And if you don't have anyone else that understands it better than you, then you really need to dive very deeply into this. So another problem that we had was the fact that in one representation you have this mu vector here, and in another you don't have. And well, in the paper they mentioned that you can incorporate this mu into the sigma, so you will have like a modified sigma, but it wasn't obvious how to do this, whether we need to do this, and how to account for that. And also the representation that they have in the diamond package actually kind of already have this incorporated into the matrix. So it took some time to kind of understand how do we want to deal with that. And actually, this wasn't a big problem, but this was, I had two problems. So this like SDP confusion, and also this how to tackle this me term confusion. And two of them, they just, well, made me waste significant amount of time trying to figure out what's going on. But finally, we managed to do that. And we written the code. And this is how the code looks like. So if you take a look at this, this is actually not that much of the code. So this is for the case of semi-positive, positive semi-definite. So you can see that like here is SPD matrix. It's actually wrong abbreviation. I should fix that. It should be semi-positive definite, and it should be positive semi-definite. So you see like the kind of traces of my confusion even here in the code. Yeah, I notice it right now, so I will fix that. But you see that this is actually pretty simple code, because this is actually a pretty simple problem. There is a little bit of bookkeeping to translate the problem into the format that the CP, which is CVX how it works. And also we had another version of this function where if the matrix is not definite semi-positive, positive semi-definite, then we just use a classical optimizer with constraints, and we solve this. So that's the code. There are also associated tests with that, of course. And there are a couple of issues with the code that I've written. So one was that there were some, I thought that it's all done, but actually it wasn't, because for one, there was like numerical errors. So it turns out that if you use the optimizer, a regular optimizer with constraints to do this, you can get values like 1.0002 or -0, basically. And this is bad because in order to translate those solutions to thetas, you are using arcsinus function, and well, it doesn't like values outside of like 0, 1. So it was throwing some errors. So, well, it was a bug. I added a rounding here to make sure that if we have some numerical imprecisions like this, then we'll get our value rounded. But at the same time, if actually it's not due to numerical imprecisions, but something that's more significant than 8 decimals, then it will just return whatever we wanted. Well, there were some issues with running it on Orquestra, and I had to debug that. And also, it turned out that the way the problem is defined, this part of the code which solves the problem for the positive semi-definite matrix actually always returns a vector of zeros, no matter what's the input, just from definition. So we just realized that actually we didn't even have to wonder whether to use CVXPy or CVXOpt, because it will, no matter what you use, you will always get a vector of zeros. We decided to leave it the way we have already written that, because it's not very computationally intensive anyway, and might be useful in future if we decide to modify it. But it was quite a surprising realization at some point. So since I don't have too much time left, lessons learned. So, well, implementing algorithms is hard, and I thought this will take me about 2 or 3 days, because I just looked into the paper, I looked at the Ansatz. The Ansatz looked easy, and I thought, yeah, that's easy task. But it actually took me more like 7-8 days of work so roughly 2 weeks. You can, well, I also estimated, like have not estimated it properly, the amount of work, because I had convex optimization when, on one of my university courses, and I basically knew more or less how it works. But actually that was a good couple of years ago, and as it turned out, I didn't really remember very well how to deal with that. So I needed some refresher. And it's a good lesson for me that, well, the stuff that looks familiar because you had that knowledge a couple of years ago doesn't mean that you still have this knowledge. And maybe it's more complicated than it looks. And also this, as I mentioned, this shows how important it is to work closely with someone who actually understands the domain of the problem, understand the science of the problem very well. Because, well, this gave me the comfort that I didn't have to read the paper in, very detailed way, and I didn't need to actually understand all the details of what's happening there, because I could always ask Guoming. On the other hand, if I was to implement it by myself, I would definitely spend much more time, learning about the problem and understanding it much better. So, well, that's it. I guess that's the last slide. So just to give you a little bit more idea of what are some other things that I've been recently working on, which are maybe not necessarily, as algorithms oriented. So one thing was translating between weighted poly operator in Qiskit and qubit operator objects in OpenFermion, with the link to the code. There was one task where, with my friend Alex, we were adding different graph problems than just MaxCut to our library. And like he was mostly coding, I was just helping a little bit. Then actually, in order to write the code that you've seen, I had to refactor the whole Ansatz, like the tests for the Ansatz base class, because the tests were written in unit tests and we are now using PyTest. So I just had to go and like fix all tests. There were some, bugs in the conventions of the QUBO that was, well, that's, I can talk about what happened here for another hour, I guess. That was pretty confusing as well. And apart from that, a lot of other things like simplified typing, a lot of design discussions, decisions about how do we want to release our software, how you want to perform serialization and other stuff. I've added GitHub actions for automatic style checking and things like this. There is a lot of writing internal documentation and guidelines recently, and also like just improving some internal processes. So that just to give you, better sense of what I've been working on in the last month or 2 months, except for this warm starting QAOA. And also I wanted to once again emphasize that, it's all team effort. And I couldn't do like any single of, well, maybe not any single, but like most of this tasks here involves more than one person, more than me. And I, for example, with this debugging QUBO conventions, I was getting a lot of help from Conrad, who has much more experience with QUBO and Ising problems. Here I was doing this with Alex. And for example, with this weighted Pauli operator, I was discussing how we want to handle that with both Max and William on our team, because Max knows, he knows our code base better and the OpenFermion package better, while William has more knowledge about the Qiskit. So, I asked them. So, it's all team effort. And I don't think, and I think it's super hard, especially in quantum computing, to be a lone kind of developer. just because there are so many things and the science of all that is so vast. Okay, so that's it. And I wanted to ask if you have any questions.
So thank you. Yeah, so I'm reverse again, but there's nothing I can do right now. So thank you for your presentation, and we have some questions that we would like to ask from our attendees. So the first one is that which platform do you work on, Qiskit, Microsoft Azure, or something other, and why do you prefer that one?
Sure. Oh, so I will answer just like I forgot. If anyone is, you just forgot to say, like you can find me here. You can find me on Twitter as well. I'm sometimes throwing some, content interesting. If you like this, then I'm also publishing some interesting content there. So you can also find my blog and podcast through my Twitter. So just wanted to make sure that if anyone is looking for more information about it, they can find it there. Answering the question, well, we are actually, regarding that, we are platform agnostic. So we have our own circuit class, which translates between Pikewell, Qiskit, and Circ. And the way we designed Orquestra is that you can use, you can write your code in any of these languages and just translate it to another one or translate it to like the format that we are using. And that's it. So it's like doesn't matter really what platform you are using. I personally prefer to use Pikewell for like my personal projects or like for small prototypes, but that's mostly because when I started doing quantum computing about 2 or 3 years ago, Pikewell was much more user friendly, and I just like started from Pikewell, and I know it best. But I think that's like just my personal preference, and there's like I don't have a very strong reason why I use this like Pikewell in favor of Qiskit or Circ, rather than just like me being familiar with that.
Okay, so we have some research-related questions that I want to ask first. So on the specific topic that you talked on, so how do you design the mixer Hamiltonian in the case of QAOA?
Okay, so one moment. Okay, so basically, it is designed like it's described here how you design the mixer Hamiltonian, and here is the equation. I don't have really anything more to add here. So here's the equation, and here is the how this equation translates to a circuit. And I guess that's it. I mean, like you can read more about this in the paper why they did it in this particular way. But yeah.
Thank you. So another one related. So can we consider QAOA as a variant of quantum alternating operator Ansatz algorithm?
Can we? Could you repeat?
Can we consider VSQAOA as a variant of quantum alternating operator Ansatz algorithm? I can send you in the chat also.
I know what you're referring to. Thinking. I don't remember the definitions that Stuart used in his kind of paper where he described this. I think so, in principle, because the alternating oh, always forget the name, but like I will refer to it as like Hatfield's QAOA. So like Hatfield's QAOA is, as far as I remember, a generalization of the regular QAOA, and it just gives you more freedom over what you do with the mixer Hamiltonian and the initial state. And well, this is what we see here, like you know, more freedom around it. But I'm not sure for the one reason, which is that actually the most of the Hatfield's paper about most of the examples that he gave were the examples where he was starting from a feasible solution to a problem and then designing the mixing Hamiltonian in such way that it allows you only to produce other viable states, right? So if the, I don't know, this viable solution to a problem is a state where you have only zeros and just one, then the mixer Hamiltonian would transform the state that looks like this into another state that has one but in different position. While in here, we actually, it's more complicated because you have those states that are like rotated by Ry. And you can get an arbitrary, I mean, not any state, but you know, like a lot of different states that are not feasible solutions to the problem because they are superpositions. So because of the rotation. So actually, I'm not 100% sure whether you can treat this as alternating layers or like Stewart's, like Hatfield's QAOA. I think so, but I would need to check the paper and the definitions to say that with kind of more, how to say that, confidence.
So thank you. So another one related again. So for which optimization problem did you implement worm starting QAA, and how is the performance compared to ordinary or other variants of the QAOA?
So the beauty of what I'm doing is that I have no idea because I was just implementing this and Guoming is doing research. So I don't know. I don't know what problem he is. I mean, maybe I do know, maybe I don't know, but maybe I shouldn't talk about it publicly. So he is doing it for some problem, and he decided that this method will be a good method for this particular problem. And I'm not sure whether he already started actually running any simulations or tests with that. But this is like important distinction between, like, I like this question because it shows the distinction between actually being a quantum software engineer and being a researcher. I just implement it, and now it's the work of the researcher to use it and just run it on 1 billion different problems, instances, and tell me whether, you know, its performance is good or bad. But like, that's not my job to tell that. Like, my job is to provide a code that, you know, allows them to run the experiments. Yeah.
Thank you. So I have another question, and I will send you the question also via the chat because it's a long one.
Sure.
So does your recent implementation on the worm starting QAA meet the conditions for providing quantum speedup that was recently published by a group in Los Alamos? Maybe you have seen it or not. I don't know.
I don't remember. I'm not sure what. I don't remember the paper that you're referring to. So I guess I can't answer the question.
Thank you. So I think that's it for the research related one, and there are more general questions also. So a question is that I probably interpreted this as, so how does a quantum software engineer or a quantum software in general relate to the devices, and how do you make it device independent?
Oh, that's a good one. So, so on one hand, I'll show you. So on one hand, the way we write the way we write software to make it device independent is that we have, again, an interface, so an abstract class called Quantum Backend, and any integration that we have, right, uses the same interface. So we have this run circuit and measure, and we have get expectation values, and for quantum simulator we have get wave function, and so on and so on. So we have a couple of methods that are same for each backend. So if, for example, we go to Zapata repo and we write QE forest, right? Or if we write QE Qiskit and we go into the simulator, we see that we have the implementation of, like, forest simulator. And here in the implementation of the specific methods, we just run, well, this is like forest code for running circuits, right? So we take this forest connection, on this connection, we translate circuit to Python, and then we basically run their code, right? And then we translate it to the same output as we are using in our framework. And basically the same is about Qiskit. So if you go to Qiskit and you select the backend, you just have regular, okay, so let's see where this is defined. Right, you have kind of Qiskit code for doing that. So I'm not very familiar with this code, but basically this, like, oh, it's actually more involved than I suspected. Oh, but we have like we create like some IBM jobs, and we have job, execute, whatever there is, right? And the thing is that one way of doing this device independent is having these connectors, these interfaces. So, well, I can now just use my backend class, and as I have it defined here, right, I can run circuit and measure and get the results. And no matter which backend I'm using, I'm using the same format, and I'm getting, it's like uniform. So it's super convenient because it allows me to do later do stuff like, one moment. Okay, not here. So just going through the code base in the real time might be confusing, but I think we have it here. Okay, I will just backend. Okay, so then if we want to calculate estimate the expectation values or whatever, we can take the backend object and run circuits and then measure on this backend, right? So actually, this code here is agnostic to what backend it's running on, as long as like the backend conforms. So I don't have absolutely any Qiskit or Python code or circ or whatever else code here in the logic that is about estimating the expectation values, because this is being done in the backend. So I separate my code like logically with respect to that. So that's a great thing. This is like one layer of making that device independent. And why I know it's a great thing, because we actually started long time ago. We had a code which wasn't like as separated, and we had a function like here. You would see 5 if statements for 5 different platforms that we had, and that wasn't either easy to use or debug or manage. So that's one layer. But the other is, well, you can only be device agnostic up to a point. So if you are running something on the real hardware, you right now with the NISC devices that we have, right now we just have to design our circuits in a way that's designed for a specific device usually, because the compilation of the gates alone just adds too much overhead. So usually what you do is you know on what device you want to run your code, right? And then when you write a circuit for that, you just make sure that this circuit is compatible with this device, so that you don't for example, use gates that you shouldn't, and you only connect the qubits that you should be able to connect, and things like this. So it, like, on some level it's device agnostic. On some level you still need to kind of make sure that your circuit, that your code is actually written for a specific device.
Thank you. So I have another one long question to you. So there's hope that quantum computing could find applications in finance and in banking and economics. So do you see anything? You can hear me, right? From the noise.
Can someone mute themselves? Or
it's myself.
Okay. Sorry. Then okay, that's good.
Yeah, I'm sorry.
Oh.
So there's hope that quantum computing could find applications in finance and banking. And from your experience, how close are we to seeing QC applied in finance and fintech industry? And are there any low-hanging fruits that we're close to getting? And also, how we can, there's a second part of the question, so we can ask that later on.
Okay, so I answered this one. Well, I don't know, because I'm not working on anything finance related, and I just have no idea. And like, finance is not really something of interest for me, so hard to say. And also the other thing is that actually it's, like, it's all speculation. I laugh that when I get into quantum computing about, I think about 3 years ago, people were saying that, well, quantum computers will be useful 2 to 5 years from now. And actually this haven't changed. So today people are also saying that they will be useful 2 to 5 years from now. And no, it's just super hard to say. So the like, not to leave you kind of with this non-answer, I think that we will see pretty soon some proof of concept solutions that could actually prove some advantage of the quantum algorithms versus the classical methods, but on the problems that are, either too small, too big. So if you take a look at what Volkswagen did, so there's a couple of papers from Florian Neukart's group at Volkswagen. They spent a lot of time working with the logistics experts, from like the transport experts, to get to just like frame the problem in the right way, and like define the problem properly, and find the problem where quantum could help. And they took that and they combined it with their kind of expertise in the quantum computing optimization. And out of that, they came up with some interesting algorithms. But the problem is that these algorithms are not easy to generalize to be used in any other context than what they proposed, because there is so much assumptions and so much domain knowledge about the problem knowledge just like baked into the algorithm itself. And I think we can see things like this more like sooner, and this could be even production solutions. Like, hard to say, like, really, like, I have no idea. But this is possible. Just the usefulness of that will be extremely limited to like this particular use case that they had in mind while designing the solutions. But this can also change pretty quickly given the rapid development. But that's like kind of how I like to look at kind of quantum computing being actually used for anything useful in the near term.
So thank you. There's also a second part of the question, which is that how could we go about building in-house software engineering expertise within quantum computing? Are there any work examples that you would point us to?
Okay, so the question is, I guess, what the we means here. So if the we is about individuals, then I guess just learning this and doing project and implementing papers, contributing to the open source is a great way to build like in-house, like your own kind of expertise within quantum computing. And we have a lot of examples of that at Quantum Open Source Foundation, QSF, with the mentorship program and others. But actually, probably in-house means in-house in some company, actually. So it's hard because it depends. Like, okay, it depends on the company. Because if you are, it requires time and effort to do that. So if you are a small company and you just want to, be ready to use quantum computing, you might not have actually resources. You might not have enough people to allow a couple of people to just work on quantum computing projects for significant amount of time so that they gain this expertise, right? But if you are a huge corporation, well, you can easily allow for creating a quantum computing team within your organization that will be working on this type of POCs and projects. So, well, that's like on one perspective. But I think that the best way to get this expertise is to work. Okay, and I'm definitely might be biased here, but I think it's to work on the projects that are relevant to your industry and to the problems that you are working on kind of on a daily basis. And this is pretty uncontroversial, I guess. But the other thing is actually trying to get into partnership with some quantum computing companies and do a proof of concept project with them, because you can, like, it's, the field is really like this is really hard. Like the quantum computing is really hard, and to get all the pieces right, it just takes a lot of time and effort. And trying to do all by yourself, if you don't have an in-house, like, very good expertise already, it just hard. It just takes a lot of time just to express your problem in the Ising Hamiltonian terms, for example, right? Or figuring how to do that properly. So if you can partner with someone who actually knows the quantum part better, then you can work together on some proof of concept project, and then you will learn a lot about quantum computing in process, and especially about kind of the applied part, while at the same time the more quantum computing company will probably learn more about your domain, and they will be happy to just like learn how to apply quantum computing to this particular type of problems. Worthy examples, oh my. So I would say that we had at Zapata, there was this paper that we did in cooperation with BP, and I know like we learned a lot, and I guess they also learned a lot in the process. So that's one example I can easily think of. I think what we did at BOR was also, so before joining Zapata, I was working at BOR Technology, a startup, it's a very small startup, and we were basically trying to solve vehicle routing problem with quantum computing. So we had a pretty concrete problem with pretty concrete kind of constraints. Like we had like the problem was defined, and we knew that we don't want to try to solve all the variants of the problem, just like, you know, this specific variant. And then we just tried to figure out how to solve that. So just like focusing on a very specific problem and not trying to, you know, solve all the problem from the broader class or whatever. Just like take your assumptions, however realistic or unrealistic they are, just stick to them and don't bother about it, and just try to squeeze most out of that. Yeah.
Thank you. So I think that was all of the questions. So thank you for coming, and we will take a small break now, and thank you for coming again, and thanks for this great presentation and sharing your experiences with us.
My pleasure. And if anyone actually has any other questions that they will come up later, you can easily find me in the internet and just send me an email or message or whatever. I'll be happy to answer.
Thank you. So we will take a small break right now and then move on to Dr. David Lee.
Thank you very much. Have a nice day.
Have a nice day. Thanks for coming.